So, hi everyone, thanks for coming. So today I will be talking about the index of symmetry of a Riemannian manifold. This is a notion introduced by Olmos, Reggiani, and Tamaro in 2014, I guess. Maybe the original paper was in 2013. And then there were further developments together with my supervisor, Jürgen Berndt, several years later in 2017. So I'll introduce this notion and talk about some of their results. I won't be able to talk extensively and discuss their methods, at least in depth. So it is planned to be just an introductory talk. Okay, So here's the plan. This is the plan of the talk. First, I'll give some introduction and motivation, which is going to be about symmetric spaces. Then I'll define the index and foliation of symmetry. Then I'll introduce some classes of Riemannian homogeneous spaces for which it is in general easier to compute the index and foliation of symmetry, because in general it's very hard. And finally, I'll talk about some known results. My references will be just these two papers that I mentioned. So the index of symmetry of compact natural reductive spaces and compact homogeneous Riemannian manifolds with local index of symmetry. Okay, so here's the intro and motivation. Basically, it's all about symmetric spaces. So let me remind that the Riemannian symmetric spaces are one of the most well understood classes of Riemannian manifolds, because they can be studied extensively in terms of Lie theory and Lie algebras. So they were classified by Cartan in the something like 1926. So recall that a connected Riemannian manifold is called symmetric if at every point of the manifold there exists, for every point of the manifold, there exists an isometry that fixes this point and whose differential at this point is just -1. In other words, this fixed point, in other words, this S is an involution and P is the isolated fixed point of this involution. Or in other words, it just reverses geodesics through this point. Symmetric spaces are automatically homogeneous and much more than that. So usually the notation for symmetric spaces is as follows. If you have a symmetric space M, you define G to be the connected component of the isometry group. The isometry group is a Lie group, so you can take its connected component. And Gothic G to be its Lie algebra. Because M is automatically complete, it's the Lie algebra, the isometry Lie algebra Gothic G coincides with the Lie algebra of Killing vector fields. Or in other words, there is a natural map between them, between the isometry Lie algebra and the Lie algebra of Killing vector fields, which is an anti-isomorphism. We'll define it in a bit. We usually pick a point O, which is a base point, and then let K to be the isotropy group, the isotropy of G at the point O. And let Gothic K to be its Lie algebra, which is a subalgebra of G. So this way we can realize M as a quotient of G by K. And finally, the conjugation by SO the conjugation of G by the isometry SO, which is called the geodesic symmetry, provides an involutive automorphism of G, which we call big theta. In the formula is G goes to S0, SO, SO. And it's on the Lie algebra Gothic G, there is the induced, also involutive automorphism. We call it a small theta, which is just the adjoint of SO. Okay, so what's going to be important for us is the so-called Cartan decomposition of the Lie algebra G, K plus P, where K is the subset of vectors, subspace of vectors where theta is just 1. And P is the subset of vectors where theta is -1. Because theta is involutive, its eigenvalues are just 1 and -1, and G is the sum of these two eigenspaces corresponding to 1 and -1. And the most important part here will be the relations between K and P, so that the Lie bracket of K with itself or of P with itself lies in K. whereas the Lie bracket of K and P lies in P. The latter, that the K of P lies in P, basically means that P is a K module or a representation of K. And the fact that the Lie bracket of K with itself lies in K just means that K is a subalgebra, which you already know. We will be referring to this as with this like red star. Okay, so yeah, and now the main result about symmetric spaces that we'll use as a motivation for what is yet to come is let's talk about it. So if I have, as I mentioned, the isometry algebra and the killing algebra are the same thing. If you have a vector in the isometry algebra X, then the corresponding killing vector field can be defined like this. Well, here's the definition for the point P. You define it in terms of the one parameter subgroup of the isometry group that corresponds to X. And there is an alternative definition which will be useful to us. So if we write, I always confuse eta with something, with some other, like tau, I think, letter in the Greek alphabet, which is embarrassing. So yeah, this is eta, hopefully. So eta P is just the orbit map from G to M, which sends G to its value at P. And then the differential of this map at the identity maps the isometry algebra onto the tangent space to M at P. And the value of our vector field, killing vector field X star at P is just we need to take X in G and send it to TPM along this linear map. This means that the value of all possible killing vector fields, and this works for a general complete Riemannian manifold, the value of all killing vector fields at a point together, if you just evaluate all of them together, they will give you a subspace, which will be precisely the tangent space to the orbit of the isometry group through this point. This will be essential for us later on. Yeah, and because this map from G to TPM is surjective, because our manifold is homogeneous, it stands and its kernel is precisely K. We have an identification between this P summoned and TOM. Okay, so and now the main part. So the standard fact that we need is that K and P can be described in terms of the killing vector fields like this. K consists of those vectors X in G, the value of whose corresponding killing vector field at O is 0. And P consists of those X's such that if you take the killing vector field X star and compute its covariant derivative with respect to the Levi-Civita connection, the corresponding covariant derivative at O will be 0. Okay, so we conclude, because we know that P, that if you project P onto TPM, this will be TOM. This will be the entire tangent space TOM. This means that for every vector tangent to M at O, there exists a killing vector field whose value at O is our vector V, but also whose covariant derivative at O is 0. Right? In other words, every vector, tangent vector to M at O extends to a killing vector field whose covariant derivative at O is 0. Well, this is the main characterization. And the main fact here is that this property characterizes symmetric spaces, which we'll now discuss in a bit, and then we'll proceed to like the main part of the definitions. Are there any questions so far? Okay, so let's move on. So here's our fact, which is kind of the converse of what we just said. If you start with a connected, complete Riemannian manifold, and you know that there exists a point O in it, and such that for every tangent vector V at O, there exists a killing vector field whose value at O is V and whose covariant derivative at O is 0, then M is a symmetric space. All right, so this is basically the converse. Now I'm going to sketch a proof of how to prove this. There will be some technical parts which I will omit, but I'll prove some of it. So we define G, K, Gothic G, and Gothic K as before. And we also note that in general, even though if we don't know yet that the M is a symmetric space, K is precisely those elements of the Lie algebra G whose corresponding such that X star at O is 0. This is very easy to show. This is standard. And the step 0 is that because M is complete, as I already mentioned, G is anti-isomorphic by means of this map, X goes to X star, to the algebra of Killing vector fields. So our fact is indeed the converse of the conclusion in the previous page, because if you remember in this conclusion, we talked about existence of elements in G whose corresponding Killing vector field is such that blah, blah, blah. Whereas in this fact, we say that there exists a Killing vector field X such that blah, blah, blah. Well, because Killing vector fields and elements in the algebra, in the isometry algebra are the same, these are indeed two converse propositions, assertions. So we can think of this as a Killing vector field, or we can think of this as a vector in the isometry algebra who has a corresponding Killing vector field. Okay, step 1 is define P as those elements in G whose corresponding covariant derivative of the corresponding Killing vector field at O is 0. Now, it is important that this P is a subspace and it doesn't intersect with K, because if you have a Killing vector field whose covariant derivative at the point is 0, and also whose value at this point is 0, then this vector field must be 0. Well, this is pretty much the Lie algebraic version of the fact that an isometry of a Riemannian manifold is defined by its value at some point and its differential at some point. This is a standard fact from differential geometry. So they do not intersect. And we also know the following: because P lies doesn't intersect K, its dimension is less than the dimension of G mod K. But G, the Lie group G mod K, mod the Lie subgroup K, is precisely the orbit of G through O. So so we have this equality in the middle, and then the orbit, we do not know yet whether the M is even homogeneous. So the orbit is in general less than or equal. The dimension of the orbit is less than or equal to the dimension of M. But look, now we know that basically there is we can restate our assumption about the existence of such Killing vector field is that the image of P under the mapping, which is just the differential of the orbit map from G to TOM, is the whole TOM. It means that every vector in TOM can be extended to a Killing vector field whose covariant derivative is 0. Basically, it means that the dimension of P, which is the left-hand side here, coincides with the dimension of M, which is the right-hand side here. So we have two equalities here between dimension of P and dimension of G mod K, and here between the dimension of GO and dimension of M. So this gives us two facts. One, GO is just M. It follows by connectedness of the manifold. So M is a Riemannian homogeneous space, which is already a huge progress. And also that G is actually, not only K and P do not intersect, but they span the whole G as a direct sum. Okay, now step 2 is to show that there are the relations between the Lie bracket relations between K and P are the same as in the symmetric case, which is the bracket of K with itself lies in K. We already know this because K is a subalgebra. So we need two more relations. K with P lies in P, and P with P lies in K. Okay, let's deal with the first one. I claim that that P is K invariant with respect to the adjoint action of K on the isometry algebra G. Well, here's how to compute it as just a one-liner. We take X lying in P, we apply the adjoint of K, and then we want to show that it's covariant. If we take the corresponding Killing vector field, then its covariant derivative at O is 0. Well, let's compute its covariant derivative in the direction of some vector W, which is tangent to M at O. This is a standard fact that if you take X, apply adjoint K, where K is some isometry, and then take the corresponding Killing vector field, this is the same as to take the corresponding Killing vector field to X, and then just push it forward with respect to the isometry K. Okay, but now isometries, they kind of commute with covariant derivative, which means that it's the same as we apply K star to the whole covariant derivative. But then instead of W, we need to write K star inverse of W. But now we know that the covariant derivative of X star at O is 0 with respect in any direction. So this is just taking K star of 0, which is 0. So P is big K invariant, and therefore it is small K invariant. So the Gothic K, its bracket with P lies in P. So have done. And we also need to show, which is easier, that the bracket of P with itself lies in K. This is easier because, look, we take two vectors in P, X and Y. We compute their Lie bracket, and then we need to show that this lies in K. Vectors in K are precisely those vectors such that if you take the star of them, the killing vector field, then at O, this will be 0. So let's compute that this is 0. As I mentioned, taking the star, so going from the isometry algebra to killing vector fields, is an anti-isomorphism. So we can put the stars inside the bracket, and this will give us the minus, which is just to swap the factors. But now, because the Levi-Civita connection has 0 torsion, this is the same as to compute nabla of X star in the direction of Y star minus the opposite, and to compute this at O. But because X and Y both lie in P, their covariant derivative at O with respect to any direction is 0. So both summands are 0. Okay, but this is great because now we have K and P, and they satisfy the relations red star, which we want. In other words, if you just define theta to be a linear map from G to itself, which is +1, which is identity on K, and -1 on P, this will be an involutive automorphism of G, of our Lie algebra. So we've almost arrived, well, almost, actually not almost, because the main part is still, the technical part is still ahead. But we see that we kind of arrive in convergence to the fact that M must be a symmetric space because it's homogeneous, and now we have its decomposition of its isometry algebra, just as in the symmetric case. The step 3 is just how to proceed, but then the technical part, I'll have to omit it because it's very technical. So we kind of want to lift this small theta to the level of Lie groups. In general, it's difficult to lift to G, but so this is what one does. You take G tilde to be the simply connected Lie group with Lie algebra G, and then you lift theta to the big theta on tilde G. This is always possible because tilde G is simply connected. And then you take K tilde to be you take the set of fixed points, the subgroup of fixed points of big theta on G tilde, and then you take its connected component of the identity. So this is a standard part of symmetric spaces and how you present them with symmetric pairs, that G tilde mod K tilde is nothing but the universal Riemannian covering of M. And because you can represent it as G tilde mod K tilde, which comes from some big theta, from some involutive isometry, M tilde is a symmetric space. So M itself, we don't know yet whether it's a symmetric space, but we know that it's homogeneous and its universal Riemannian covering is a symmetric space. In particular, M is locally symmetric. And then the Riemannian piece, which is the technical part, which I'm going to omit, is that the geodesic symmetry, you remember the one which we call SP, which reverses geodesics, of M tilde descends to M. This is technical, so I'm going to omit it. So now we can proceed to the main part. Now that we know this characterization of Riemannian symmetric spaces, we'll use it as an inspiration to measure how badly a given Riemannian manifold fails to be symmetric. Are there any questions so far? Great. So yeah, here's what we do. We just take any connected complete Riemannian manifold, and then we take G to be the identity component of its isometry group, which is a Lie group, and we take Gothic G to be the isometry Lie algebra, which is the same anti-isomorphism, remember, that the killing Lie algebra. And we also pick any point Q in M. And we kind of do the thing we did in the symmetric case. Let's write, now we will refer to the point Q, PQ as those elements in G whose covariant derivative of whose corresponding killing vector fields X star at Q is 0. And instead of writing for KQ the isotropy Lie subalgebra at Q, we will instead just write the bracket of PQ with itself as KQ. So we'll see in a second that this is not the whole isotropy Lie subalgebra at Q, but something smaller in general. It's not essential, I think, but we just don't need the remaining part of the isotropy Lie algebra at Q. So we will only be using this Lie bracket of PQ with itself. So if you write K for the isotropy group at Q, and Gothic K, with no reference to Q here, just to distinguish from the KQ we defined for its Lie algebra, then you know that K and PQ don't intersect. The same reasoning. If you have a vector field, killing vector field, whose value at Q and the value of whose covariant derivative at Q is 0, then it's 0. So they do not intersect. Now the difference is that you have this summoned K and you have this summoned PQ. They no longer in general span the whole isometry Lie algebra. They're just separate pieces. They don't span it, of course, unless M is symmetric. Okay, and now the same computations as we did on the previous page show that PQ is K invariant, where K is the isotropy subgroup. So this means that, so we know that PQ is K invariant, and we also know that KQ lies in K. The same computations, because KQ is the bracket of PQ with itself, and we computed on the last page that it must lie in Q, in K, sorry. So we know that overall, we have the K piece, the PQ piece, and we know that the bracket of PQ piece with itself lies somewhere in K. Okay, so we take the KQ, which is the bracket of PQ with itself, and PQ, and consider their direct sum, which is some Lie subalgebra of G. The fact that it's a Lie subalgebra, it's just direct computation. It's basically because we define them in this way. And we also know that these two pieces, which are subspaces of GQ, they satisfy the relations of the symmetric space. The bracket relations between them are precisely as in the case of symmetric spaces. Okay, but because this is a Lie subalgebra of G, of Gothic G, we can define big GQ to be the corresponding connected Lie subgroup of G. Great, we're almost done to define everything. Just one small remark, that if you take X to be in PQ, then you know that X star is first of all a killing vector field. And you also know that its covariant derivative at Q is 0 by definition. From this, it's not hard to see that the integral curve of this killing vector field, which is just the orbit of Q under the one parameter subgroup X of Tx, is a geodesic. Okay, this is always the case in the symmetric spaces. This is a standard fact. And the last thing we do is that we define SQ to be just the image of PQ under the map from G to TQM. They're of the same dimension. So basically you have this K piece, which is the kernel of this map. And you have somewhere not intersecting with it, the PQ piece. So when you project it onto TOM, this will project, you will project isomorphically onto SQ. So now SQ is some subspace of TQM. Any questions here? Okay, so here's the definition. The leaf of symmetry of M through Q is the orbit of this group GQ through Q. We denote it as LQ. Okay, and the index of symmetry of M is the minimal possible dimension of this subspace SQ. It's pretty much straightforward that SQ is the tangent space to the leaf of symmetry L of Q at Q. So in other words, the index of symmetry is just the smallest dimension of a leaf of symmetry of M, right? And this is a number from 0 to n, where n is the dimension of the manifold. Okay, and finally, just the technical additional definition. The co-index of symmetry is just the dimension of n minus the index of symmetry. Okay, and here are the main properties, which are almost all very straightforward. First of all, the leaf of symmetry is an immersed connected submanifold of M. It's immersed and connected because it's an orbit of GQ, which is a connected Lie subgroup. And next, we claim that it's complete and totally geodesic. The reason for this is what we had in the previous page, this remark, that if you take X in PQ and you look at the orbit of Q with respect to the one parameter subgroup XTX, this will be a geodesic. And by construction, it lies in the leaf of symmetry. So basically, the leaf of symmetry consists of, you need to take the tangent space SQ, which we've defined here, and just map it with the exponential map. In general, if you take some subspace of the tangent space at some point of Riemannian manifold and apply the exponential map, the image will be horrible. It may self-intersect, it may be degenerate at some point, it won't be a submanifold. But in this case, we know that this will be an orbit of some Lie subgroup. So this is a nice, immersed, in general not closed, submanifold, and it is complete and totally geodesic. Okay, and the best part is that it is a symmetric space. And the proof is pretty much what we did before. We already have this decomposition, GQ is KQ plus PQ. We already have the relations between them. So basically, we can just say that at every point, at every point of the leaf of symmetry, and for every tangent vector at this point, there exists some killing vector field on the leaf of symmetry, which is has this value at this point and whose covariant derivative at this point is 0. Why? Because such a vector field exists on the whole manifold, and then we just restrict it to the leaf of symmetry, and this restriction is a good operation because the leaf of symmetry is totally geodesic. So this is a symmetric space. Also, we need to mention that this is a good notion because it's invariant and functorial, because if you have any isometry of M, then you do the following. You take the point Q, you map it with this isometry, and then you look at the corresponding subgroup GHQ. This is the same as to take GQ and just conjugate it with oh, sorry, it should be not small g here, but small h here. It should be h, GQ, h minus 1. In particular, this means that your isometry H, if you take your isometry H and apply it to the leaf of symmetry LQ, this will be just the leaf of symmetry at the point HQ, which kind of a good, so the notion of leaf of symmetry is good because it's kind of invariant. So if you have basically two Riemannian manifolds that are isometric, any isometry between them maps the leaves of symmetry here onto the corresponding leaves of symmetry here. And also from 3, it immediately follows that if you have, so this is kind of a very stupid thing that you still need to check right away, that if you take Q, take the corresponding leaf of symmetry and go to some other point on this leaf of symmetry, its leaf of symmetry will be the same submanifold. It just follows from 3. So it gives you kind of an equivalence relation on your manifold. Basically, it gives you a foliation of your manifold into pieces, which are symmetric spaces. The only problem is that they may be of different dimensions. So in general, it's not a foliation. It's kind of a singular foliation. And we also know, we've already showed this, that the co-index of symmetry of M is 0. In other words, the index of symmetry of M is maximal, the dimension of M, if underneath M is a symmetric space. We showed this at the beginning. And finally, if M is a homogeneous Riemannian manifold, then its leaves of symmetry are all of the same dimension because any leaf of symmetry is mapped onto any other leaf of symmetry by corresponding isometry. So all the leaves of symmetry together form a genuine foliation where each leaf has the dimension which is the index of symmetry of M, and we call it the foliation of symmetry, not surprisingly. Any questions at this point?
I have one question.
Mm-hmm.
Is it true that the foliation or singular foliation is induced by a homogeneous foliation is induced by a Lie group action or not?
In general, here the answer is no, because these are different. For each leaf is the orbit of a different Lie subgroup. Okay. So in general, no.
Okay.
Mm-hmm. But that's a good question. Thank you. That's kind of the thing that I mistook it for something which comes from the same Lie group myself when I started preparing this. Okay, so here, rather than if in the homogeneous case, you have each leaf of symmetry is an orbit of some subgroup, and then if you have another leaf of symmetry, this will be maybe another subgroup, but it will be conjugated to this one. Okay, so here's the basic construction. Almost any complete connected, we need to add this. Riemannian manifold can be decomposed naturally and functorially and nicely and invariantly into leaves, into pieces. Each of them is a nice, totally geodesic, homogeneous, externally homogeneous submanifold and also a symmetric space. So this is kind of a measure of how badly M itself is not symmetric.
Sorry, you said that it's intrinsically homogeneous or homogeneous.
Yeah, because each leaf is an orbit of some Lie subgroup, right? Because we define here at the top, we define the leaf of symmetry to be the orbit of GQ.
Yeah, of course. Yeah. Okay, yeah.
Yeah, so it's a very nice decomposition. Okay, so now the point is we want to compute this foliation of symmetry explicitly and the index of symmetry for some Riemannian manifolds, hopefully for all of them. Well, for all of them, probably it's unfeasible, but it's easier to compute in the case of where your Riemannian manifold is homogeneous. And what's nice in this situation is that your foliation of symmetry is a genuine foliation by the same dimensional leaves. Still, in theory, in general, it's hard. So you need to restrict to some classes of Riemannian homogeneous spaces or to some special specific situations. I'm going to briefly remind the definitions for some subclasses of Riemannian homogeneous spaces for which it can be computed. So all Riemannian manifolds are assumed to be connected and complete. First of all, the Riemannian homogeneous spaces themselves, just a quick note that M is called homogeneous, the Riemannian manifold is called homogeneous if the isometry group acts transitively on it, and an equivalent definition. And I want to stress why it is different, in which respect it's different from what we had before. Complete connected Riemannian manifold M is homogeneous if and only for some point O and every tangent vector V at O, there exists a killing vector field X whose value it should be XO, not XP, is V. So every tangent vector extends to a killing vector field. The difference here is that I'm not asking this killing vector field to have the zero vanishing covariant derivative at O. That's the difference. Basically, this extension, the possibility of this extension means that the orbit of the isometry group through O is the whole M. It's an open and also closed subset. Okay, so this is the difference. And also just a standard construction that everyone does with the Riemannian homogeneous spaces, they're automatically reductive, which means that if you take K to be the isotropy subgroup of G or of the whole isometry group IM, which I'm not writing as G here for some reasons, which will be clearer later. I write the isotropy group as K because K is compact, it's always the case. Then the adjoint action, if you look at the adjoint action of K on the isometry Lie algebra, there exists an invariant, a K invariant inner product because K is compact. Every representation of a compact Lie group admits an invariant inner product. So, and with respect to this invariant inner product, we can take the orthogonal complement to K inside G and call it M. And this M will be, by obvious representation theory, preserved by K. So you can think of, and moreover, the isotropy action of K on the tangent space to M at O is the same, this is just one line computation, as the adjoint action of K on this reductive sum at M. This is called a reductive decomposition. So it kind of facilitates a lot of computations for homogeneous spaces to just Lie algebras, because you can just look at some adjoint actions and adjoint representations. So this is the general thing for many homogeneous spaces. They're all reductive, but still it's not sufficient. A nicer thing is the compact normal homogeneous spaces. Now, one remark is that you can define non-compact normal homogeneous spaces, but everyone pretty much only confines themselves to just looking at compact normal homogeneous spaces, which is what we'll do. Now, assume that the same construction is valid, but now your M is a quotient G mod K.
Sorry, Ivan,
yes?
just one question. Sorry for interrupt. Did you say that there are non-compact normal homogeneous spaces? I didn't understand this sentence.
Well, let me give the definition of a compact one, and then I'll tell how.
Ah, okay.
So thanks for the question. It's a good question. Now, the compact definition goes like this because it's more intuitive. So that's why I also wanted to restrict to this. Suppose you have a quotient G mod K, where G itself, not only the isotropy, but the G itself is a compact and connected Lie group. Then it admits a bi-invariant Riemannian metric, G. But this is the same as taking a G invariant, a joint invariant inner product on the Lie algebra G. If you're, so you do this, you take a bi-invariant metric on G, you take the orthogonal complement with respect to it to the isotropy Lie algebra K, what you call it M. And now you remember you have this identification between this reductive complement M and the tangent space to your manifold at O at the base point. So if your Riemannian metric on M agrees with this metric on the reductive complement M, which comes from the bi-invariant Riemannian metric on G, then your space is called compact normal homogeneous. Well, it's compact right away because it's a quotient of a compact Lie group. So it's kind of like, in general, in this construction above for Riemannian homogeneous spaces, your inner product on G was just K invariant. But here there are nicer metrics on M, nicer inner products on G, which are G invariant. And if you can do this with respect to them, with respect to these nicer inner products, then your metric is called normal homogeneous. Now, we can define normal homogeneous spaces if your Lie group G is not necessarily compact, but it admits a bi-invariant metric anyway. But I think it's a result of Milner that any Lie group which admits a connected Lie group, which admits a bi-invariant metric, is just a product of a compact Lie group and just some Rn, some Euclidean space when you think of it as an abelian Lie group. So, and kind of it doesn't change the picture a lot because you allow some Euclidean kind of parts. So usually people can restrict themselves to just compact case. Does it answer your question, Thomas?
Well, I didn't understand. So when you mean, because I was saying something else, sir. When you mean non-compact normal homogeneous, you mean that the metric is not Riemannian anymore, or what do you mean? What do you, because or maybe you mean by non-compact that they are abelian. Sorry, that they are flat.
No. I think it's not like, so the analogy here is not with the symmetric spaces, but just, so in general, you can do the same construction G mod K, where G admits a bi-invariant metric and obtain some, and you induce the Riemannian metric on your quotient from this bi-invariant metric on G, and G doesn't have to be a compact Lie group. There are non-compact.
Okay.
So that's
Okay. Yeah, sorry. I thought that then the manifold will have to be also compact, but it's not.
Yeah. So in general, M doesn't have to be compact as long as it can be represented as a quotient of a Lie group, which admits the bi-invariant metric. But it's kind of.
Sorry. Because all the examples I knew were compact. Do you know a non-compact example?
Yeah, just take any compact. Just take anything compact and just take its product with Rn.
With?
Take a compact normal homogeneous space and then take its product, Riemannian product with the Euclidean space.
No, but without the flat parts. Like if
no, I think if there is no flat part, then it's automatically compact. I think this is the.
Okay.
So kind of, yeah, again, if you can do slightly more general by allowing the flat part, but that's not really a progress. I don't think it's a progress. It's just you allow something flat. And I've seen definitions in some papers where people allow this flat part, but this is
okay.
Yeah, kind of a stupid case which we want to exclude.
Okay.
Yeah, thanks for your question. Okay, and finally, and then we'll give some classification results, and also the relations between these spaces. Is the naturally reductive spaces. It's slightly more involved. A Riemannian manifold is called naturally reductive if there exists some Lie group which acts transitively and isometrically on M. So we may assume it's just a connected Lie subgroup of the isometry group. We don't lose anything. And you also have a reductive decomposition K plus M of the isometry Lie algebra of G. Here K is the isotropy at some point O. So by reductive, again, I mean that this M part is K invariant, such that the following equivalent definitions are satisfied. First of all, this is a geometric one, which is, I think, just cleaner. Every geodesic emanating from O is of the form, is just the orbit of some one parameter subgroup corresponding to some vector X, but we require X to lie in this reductive sum on M, not just somewhere in G. If we were to allow X to be just somewhere in G, these would be so-called geodesic orbit spaces, which are, I think, less well understood, and they're more general. So here X must be in M. Anyone who's done a little bit of symmetric spaces know that this symmetric spaces satisfy this definition. And G, instead of G, for G you can take the whole isometry Lie group. And the algebraic definition is the following: that if you take any three vectors in this reductive thing, in this reductive complement, the following is true. Well, I just, everyone can read it themselves. So here, you take the Lie bracket of X and Y. In general, it doesn't have to lie in K because we're not in a symmetric situation. So you can still do the following. You can still project onto M, this bracket, just forget about the K part. And then you can take its inner product with Z. And this inner product is just the inner product on the tangent space at O, because we have an identification between M and the tangent space at O. In other words, for every X in M, such an operator, so you take a Lie bracket with X and then project back onto M, is a skew symmetric. Observe also that symmetric spaces obviously satisfy this as well, because if you take any two things in M and take their Lie bracket, it will lie entirely in K, so its projection onto M will be 0. So you just have 0 plus 0, which is of course 0. Yeah, this is the definition of a naturally reductive space. Note that it's important that G and M are part of the definition. So it's not really, so in order to check that something is not naturally reductive, you have to search among all possible transitive Lie groups that act isometrically and transitively on your manifold, and also to look at all possible reductive decompositions, which is quite a daunting task. So this is an involved definition. And now just to kind of see how these different things relate to each other, these are relations. You have symmetric spaces. They are naturally reductive. And naturally reductive spaces are Riemannian homogeneous spaces, which is pretty much clear from the definitions. Now, how do normal spaces fit in the picture? Because we restricted ourselves to just compact normal spaces, we can just put them here in the picture because there are some symmetric spaces which are not compact normal, because there are some symmetric spaces which are not compact and cannot be quotients of compact Lie subgroups, which is symmetric space of non-compact type, for example. So we can change the picture. If we restrict to the compact situation, then you have symmetric spaces of compact type. They are compact normal homogeneous. Those are compact naturally reductive, and those are compact Riemannian homogeneous. So many words compact here in the picture. So yeah, these are some nice subclasses. The index of symmetry, all this situation is obvious for symmetric spaces. There is nothing there to study. And it's too complicated for just this, for the Riemannian homogeneous situation. So you must look at these classes in between. That's why I've defined them. Any questions here? Okay, so finally, before I tell you the main two results, here are some examples. So a compact normal homogeneous space which is not symmetric. Take the Stiefel manifold M, which is just the quotient of SON plus K by SON, and this SON is just the n by n matrix, which is kind of sits in the corner. So you act by SON on the first n vectors, and the remaining k vectors, you just don't touch them. And you require both n and k to be at least 2 to avoid some stupid situations, and also to avoid this to be a symmetric space. Then this SON plus k is a compact and simple Lie group. Therefore, it admits unique bi-invariant Riemannian metric up to a positive constant. And it comes from nothing else but the minus the killing form on the Lie algebra SON plus k. Okay, so you have G mod k, where G admits a bi-invariant, pretty much unique Riemannian metric. So its quotient, the G mod k, is a normal, compact normal homogeneous space by definition. The only case when this thing is symmetric is when k equals 1, because then you'll have SON plus 1 not SON, and this is just the n sphere. And we've excluded the case k equals 1. This is still some, it's still some, you need to prove that if k is greater than 1, then this thing cannot be represented with some other way, and it turns out to be a symmetric space. So this is some labor, but this is just a fact that this thing is not symmetric if k is 2 or larger. Okay, and now the main results. So again, as I said, we will discuss some results when you restrict to some classes of Riemannian homogeneous spaces. And the main one is, and this is the result from the first paper, which I mentioned by Carlos Olmos, Sergio Reggiani, and Hiroshi Tamaro from 2014. If you have a simply connected compact normal homogeneous space, so here G is a compact and connected Lie group, and the metric on M comes from some bi-invariant metric on G. And you also assume two things. First, that it is not symmetric, a symmetric space. And second, that it's de Rham irreducible. This is different from isotrope irreducible. This is a weaker notion. So it just means that it cannot be decomposed as a product, Riemannian product of two manifolds. Because it's simply connected, it's just equivalent to not being able to decompose it as a product. Then the foliation of symmetry of M corresponds to the G invariant distribution defined by the fixed vectors of H. In other words, you look at the tangent space to M at O. There is the isotropy representation of your denominator H on this tangent space. And you take the subspace of invariant vectors of the isotropy representation. This is some subspace of TOM. And then you just translate it by the action of G to give it to a distribution on your manifold M. And it will be an integrable distribution, and it will be precisely your distribution of symmetry. So its integral submanifolds will be the leaves of symmetry. But there is more to it. You can describe, and this is pretty much straightforward from the construction, that the leaf of symmetry through O is just the following. You take all points of M which are fixed by H. This will be some closed submanifold, and you just take its connected component that passes through O. And this will be precisely the leaf of symmetry. And we'll see some examples later in the next page. In particular, these leaves of symmetry, in general, they're just immersed submanifolds. Here, they're properly embedded in closed submanifolds. And finally, which is a non-trivial part, just as the rest of it, each leaf of symmetry is not just a symmetric space, but a compact Lie group with a bi-invariant metric. This is a nice subclass of symmetric spaces of compact type. Okay, any questions here? Observe how tragically this falls in the symmetric situation. Because in the symmetric situation, if this thing was symmetric, each subspace of symmetry, for example, SO, would be the whole tangent space, right? In the symmetric case, the index of symmetry is the dimension. So there is only one leaf of symmetry, which is the whole manifold. So if this was true for the symmetric situation, then the isotropy representation would have to be trivial, which means that the holonomy representation would have to be trivial, which is kind of rarely the case for symmetric spaces. So this fails tragically in the symmetric situation, for symmetric spaces. Okay, and just one technical remark, we won't really need it, but you can slightly generalize this. You can assume your space to be just compact naturally reductive, which is more general, but you have to add additional restriction that if you represent it as G mod H, G is the so-called group of transfections, which means that basically if you take the reductive sum on M and take its bracket with itself, together they will span the whole Lie algebra. This is some technical assumption which I don't want to linger on, but it can be slightly generalized. That's the point. And let's look at the main example with the Stiefel manifold, and then we're almost done. If you go back to the Stiefel manifold, SO n plus k mod SON, which you think of as a normal homogeneous space, so the metric comes from the bi-invariant metric on SON plus k, you know that we need to check that it's simply connected. It follows from just the non-exact sequence of homotopy groups. It is irreducible. Well, it is irreducible. And it is non-symmetric because, as I mentioned, it is a symmetric space only k equals 1, in which case it's just a sphere. So our theorem can be applied. So if you look at on the level of Lie algebras, you have SON plus k, which looks like this. You have SON here, you have SOK here, and you have A and AT here. And SON, the denominator, it sits here as just SON here, this block. So basically, you can think of the isotropy representation on the level of the isotropy representation as SON, the group SON sitting here. It acts by the adjoint representation on this space of symmetric matrices where you have 0 here, 0 here, A here, and AT here. And it acts trivially, of course, by just how you compute, how you multiply matrices on this SOK bit. So the subspace of isotropy invariance is precisely this SOK bit. In particular, its dimension is k times k minus 1 divided by 2. So which means that the index of symmetry of the Stiefel manifold with this metric is k minus 1 divided by 2. Moreover, we mentioned that each leaf is can be thought of as a Lie group. In this case, it's obvious that this leaf of symmetry will be just the isometric to the Lie group SOK with the bi-invariant metric. Okay, because you have SOK sitting here in the last block. Note the following, that for example, if you take k equal 2, then the leaves of symmetry, then the dimension, the index of symmetry will be just 1, which means that the leaves of symmetry will be just SO2s, they will be just circles. And this is a bit counterintuitive because you make just one small step from the symmetric situation. You say, okay, let my space be non-symmetric, but as nice as possible. It's simply connected, compact, normal, homogeneous, irreducible, and very nice. And then its index of symmetry drops dramatically to just 1. The dimension, in case k equals 2, can be huge. It's something like 2n plus 1. But the index of symmetry is just 1. So it's a bit counterintuitive, in my opinion. Any questions here? We're almost done. There is just one page left. Mm-hmm.
Yeah, but here it's irreducible with respect to the holonomy representation, but
yes,
with respect to the isotropy representation, it is not. And it looks like the second factor, like the factor where the isotropy is trivial, the SOK factor is the one that matters in order to compute the index. It is like the general situation that you always have to look at the fixed vectors with respect to the isotropy representation, because I was thinking when you introduced the definition about Berger spheres, and also I think it matches my intuition of looking at the fixed vectors. Why is this? Is this easy to see, or?
So the method is fairly technical. I don't think there are in their paper there are like, you know, results which are very like conceptual. But what they do is they look at the Durham decomposition, local Durham decomposition of each leaf of symmetry, and they kind of compare the flat part of the Durham decomposition of the leaf of symmetry and this space of fixed vectors of the isotrope representation. And then they show that the and then compare them. But I don't think this is very straightforward to see from the very beginning, that this is precisely, this leaves of symmetry will be precisely the fixed vectors of the isotropy. I think there is some work to be done.
Okay, very nice. Thank you.
Okay. Thanks for the question. So yeah, that's why I didn't want to delve into like their methods, because I wasn't able to find like one or a couple of conceptual results which explain this. But yeah, so this is but you're right in saying that it's de Rham irreducible, but it's by no means isotropy irreducible, right? Because there is the subspace of invariance in the isotropy. So in a sense, this is a huge step from symmetric spaces, from irreducible symmetric spaces. Because for them, they are isotropy reducible. Here, this thing is grossly isotropy reducible because there are subspaces of invariance and stuff like this. Okay, and just the final result, and we're done. I'm a bit out of time. So another situation where you can compute this for compact Riemannian homogeneous spaces when the index of symmetry is high enough. In other words, when the co-index of symmetry is low enough, small enough, where it's 3 or less. This was done in the second paper. Let M be a simply connected compact Riemannian homogeneous space. For a second, we allow it to be de Rham reducible, but we require that none of its de Rham factors are symmetric spaces. Then the index of symmetry, the co-index of symmetry cannot be 1. It cannot be 0 because it's not a symmetric space, and it cannot be 1. So it's either 2 or higher. Now we assume that it's de Rham irreducible, and now there are these two results. If it's 2, so if the leaves of symmetry are of codimension 2, then M is homothetic, which means that it's almost asymmetrical apart from modulo some rescaling by a positive constant, to spin 3 with a certain left invariant metric. And this left invariant metric, it's computed, these left invariant metrics were computed explicitly in the paper. I won't give their construction here, but I'll just say that there are 2 one-parameter families of them. And each two elements in these families are pairwise non-homothetic. So you have like 2 lines of such matrix. And if the co-index of symmetry is 3, if the leaves are of codimension 3, then M is homothetic to SO4 mod SO2, to this Stiefel manifold. Not really Stiefel manifold, because the metric you take on SO4 SO2 is strictly different from the one we described before. Because if you go back to our construction of SO4 SO2 as the Stiefel manifold with the normal metric, then I mentioned that if k equals 2, which is the case here, then the leaves of symmetry will be just circles, whereas the dimension of this guy is 5. So the co-index of symmetry is 4. So the metrics you use here are different. But they're still SO4 invariant, and in total there is a 2-parameter family of such metrics, which are pairwise, each 2 elements in the family are pairwise non-homothetic. And this is pretty much all. Yeah, as I mentioned, this is different from the Stiefel situation. Yeah, and I think I'm done. Thanks for your attention.